entropy change of the mixture Dalton model the result of the for the entropy change of mixture shown that this relation is governed to the mixture for each component and each component mole fraction, where in component moles component mole fraction Ni on N total. The interesting thing about this equation is that increase in the entropy depends only on the number of moles of component gases and is independent of the composition of the gas. And is independent of the composition of the gas. For example, when 1 mole of oxygen and 1 mole of nitrogen are mixed, the increase in entropy is the same as when 1 mole of hydrogen and 1 mole of nitrogen are mixed. But we also know that if 1 mole of nitrogen is mixed with another mole of nitrogen, there is no increase in entropy. The question that arises is how similar must be gases be in order to have increase in entropy. This answer lies on our ability to distinguish between these two gases based on their different molecular masses. The entropy increases whenever we can distinguish between the gases being mixed. When we cannot distinguish between the gases, there is no increase in entropy. When we cannot distinguish between gases, there is not entropy increase. When we cannot, one special case that arises frequently involves an ideal gas mixture undergoing a process. For the ideal gas undergoes a process in which there is no change in composition. Let us also assume that the constant specific heat model is reasonable. For this case, we have this relation. And A for each component For component B, CB, constant specific heat on V constant volume, which is equals to CA CV0A CV0 mix. CB0. Similarly for H we can write so CB0 mix CA H2 minus H1 P. The entropy change from a single component was calculated. Before we substitute this relation, we can write S2 minus S1 where we have before determine R mix equals to CAR A RB. The last expression used in this equation for the mixture gas constant and for this heat capacities also we have relation before. This also implies that all polytropic process in a mixture can be treated similarly to the way it is done for the pure substance. Specifically, the isentropic process where S is constant leads to the power relation between temperature and pressure. This is similar to the previous equation provided before that K equals to Cp and for Cv 0 mix. We can also write this relation. So far we have looked at mixture of ideal gases as a natural extension to the description of processes involving pure substances. The treatment of mixtures for non-ideal gases and multi-phase state is important for many technical applications. For instance, in chemical process industry, it does require a more extensive study of properties and general equation of itself. We will refer this subject to Chapter 14. A simplified model of gas mixture involving gases and vapor is the next section.